In my talk, I will describe how one of the most basic concepts in optics that we are all familiar with, the interferometer, which is probably the first device that we build as new master or PhD students, can be implemented in the attosecond regime, and how attosecond interferometry enable us to obtain a very precise insight into some of the most fundamental ultra-fast phenomena in nature. But before starting, let me first begin by thanking my wonderful group at the Weizmann Institute, both current and former students. And I would also like to acknowledge ongoing, very, very friendly and successful collaboration that we have for many years with the MBI in Berlin and Bordeaux University, especially with Jan Mares, who is with us today. Special thanks also to Laserlab that enable us to travel and see advanced laboratories and expands our scientific activity. Attosecond science led to a true revolution in our ability to capture extremely fast phenomena in nature. And over the past 2 decades, attosecond spectroscopy enabled the scientists to resolve for the first time a large variety of phenomena in a broad range of systems, starting from very simple systems as atom, where we can watch the moment at which an electron photoionizes or tunnels through an atomic barrier, all the way to charge migration in more complex systems as molecules, or even subcycle dynamics in condensed matter systems. And these are just few examples out of a large variety of phenomena which all share one important property: they all evolve within a fraction of a single optical cycle of our laser field. So this is the main challenge, or the first challenge that we have to face when we try to enter the attosecond regime. How do we resolve a phenomena which evolve faster than a single optical cycle of our laser field? And let me start with the origin of this field, the moment at which we are able in our lab to generate optical pulses with attosecond duration. We can generate those pulses surprisingly quite easily by simply focusing an intense laser field into some medium, which can be gas, liquid, or even solid. And one of the outcomes of this interaction would be the production of optical pulses emitted in the XUV or even X-ray regime with one unique property. These pulses have sub-femtosecond or attosecond duration. The discovery of these pulses and their first characterization was just recently recognized by the Nobel Prize in Physics that was given in 2023 to 3 pioneers in our field, to Anne Loyer, Ferenc Krauss, and Pierre Agostini. Now, if I go back to the moment of generation, then surprisingly, we can take this interaction itself, which seems to be very complicated. It involved many, many photons. It's far from being perturbative. There's so many degrees of freedom involved here. But then we are able to take this kind of complicated interaction and describe it by very simple, almost classical tools. So here is a picture which I'm sure is familiar to many of you. In this picture, we zoom into one optical cycle, marked here by this yellow line. At the peak of the cycle, the strong laser field suppresses the Coulomb barrier and an electron can tunnel out. Once the electron is free, it is accelerated by the laser field, accumulate high kinetic energy, before eventually it may recollide with a parent ion, and recollision leads to the emission of optical pulses with attosecond duration. If we take a careful look, we realize that along the optical cycle, there are different points at which the electron can be born. And the beauty of this semi-classical picture is that it enables us to map different moments of ionization following classical trajectory or almost classical trajectory into moment of return and emitted energy. Now, in many laboratories, including mine, we repeat this entire story again and again and again because we drive it with a multi-cycle laser field. And therefore, we do not generate a single attosecond pulse. We generate a train of attosecond pulses separated by half of the laser period. And then, as we know, this periodic structure in time maps to be a periodic structure in the frequency domain, also known as the harmonic generation spectrum. So this is a typical spectrum that we can measure in the lab, where each frequency component here can be associated with an odd number of the fundamental frequency. Now, if we look again at this very simple and almost classical picture, we realize that it is a very unique mechanism. And it is unique because it enables us to integrate three very powerful aspects in attosecond metrology. The first aspect is the high spatial resolution it provides us. In principle, the electron is born, and then it must return exactly to the same point with atomic precision in order to produce photons. And any tiny deviation from this precise condition can lead to a dramatic effect in the emitted radiation. And therefore, in principle, we can probe quantum phenomena or quantum wave function with atomic precision. And then we have coherence. In this mechanism, we keep the coherent properties and we transfer it from the strong laser field into the coherence of the electronic wave function, which quickly interacts with the field. And then upon recollision, all this complex information is encoded in the coherent properties of the emitted attosecond process. And if we're able to resolve such coherence, then we can trace back the mechanism and follow the evolution of electronic wave function as they interact with the laser field. But then we realize that as we go to larger and larger systems, eventually our ability to resolve coherence, the coherence of electronic wave function, should be limited by multiple scattering or dephasing events leading to the loss of phase information. So here comes the third and probably the most important and natural aspect of this mechanism, the attosecond resolution it provides us. In principle, we probe the coherence of electronic wave function on such a short time scale where there is no scattering, there is no dephasing mechanism, and therefore we can directly approach quantum phenomena which completely smear out on a longer time scale. So it sounds very promising. We have here three important parts that combined together provides us with a powerful metrology tool. However, in order to apply all these aspects, we have to overcome one important challenge. We have to be able to resolve the full coherent properties of the emitted attosecond pulses. In other words, we have to find a way to either build or induce an attosecond interferometer. And indeed, resolving phase information has been one of the primary challenges in attosecond science since its early days. So in this talk, I will describe advanced schemes for attosecond interferometry, and I will show how these schemes enable us to shed new light or resolve fundamental phenomena which evolve during less than one optical cycle. And I would start with the most simple phenomena we can think of, the moment at which an electron photoionizes. Photoionization projects the quantum state of matter into free electron, and therefore people have been interested in resolving photoionization for so many decades. Once we enter the attosecond regime, then we can ask ourselves a fundamental question that could not have been addressed before. For example, how long would it take to photoionize an electron? Is it an instantaneous event? Are there any delays associated with photoionization? And indeed, as you can see over the past more than one decade, there have been a large number of beautiful experiments showing how with attosecond precision, one can probe the origin of photoionization. Let me go back to the same generation mechanism that I've described before. I hope I convince you it's a very precise process, and therefore a natural question to ask is whether we can use this process and apply it in order to probe the origin of photoionization. And if we take a careful look, we realize that, in fact, photoionization is already there. It's there at the very basic moment at which the electron approaches the parent ion and photorecombine. In fact, we can think of photoionization and photorecombination as the inverse mechanism of each other. They both encode the same dynamical properties, and mathematically they are described almost in a similar manner. There is one important difference between the two processes, and the difference is in the experimental observable. In photoionization, we generate electrons, energetic electrons. Unfortunately, we cannot directly approach the phase of each photoelectron spectral component. What we can do is a well-established scheme in our community known as Rabbit. In fact, Jan Mares has been the pioneering scientist that has pushed forward this technique and demonstrated it. And with Rabbit, we do not resolve directly the phase, but what we can resolve is the spectral phase derivative. And derivative are super important because they encode temporal delays. Now let's switch from electron to photons. And once we do this switch, then we realize resolving the phase is a very natural task, especially for someone who comes from optics. We know how to resolve the phase of coherent fields. All we need is a proper interferometer. Okay, it sounds like an easy task. Let's just go to the lab and build an interferometer. In practice, building interferometers that will provide us with attosecond resolution and precision is very challenging. It took us several years to accomplish that. And here is a schematic description of the interferometer that we have constructed at the Weizmann Institute with the help of Jan Mares. So let me just very briefly describe how it works. We start by focusing intense laser field. We generate a train of attosecond pulses. The two fields, the strong and the XUV field, co-propagate, reflected from a two-segment mirrors, focused again in a completely separate and decoupled gas jet, where we can generate a completely decoupled source for attosecond pulses. Eventually, these two sources interfere in our spectrometer, and once we scan their delay with this two-segment mirrors, what we can see is that each harmonic here beats, okay? And the beating is observed at the fundamental frequency of each harmonic order. Once we observed this beating, we were extremely happy because it tells us that now we have a direct access into the phase of each harmonic order, and we can take two photo recombination events, which truly represent two photoionization events, and interfere them together. So let's start with the two most simple atomic system we can think of, helium versus neon. So here are experimental results. This is the phase as a function of energy. And this is the relative phase between the two photo recombination events, helium versus neon. And as you can see, the phase is rather flat. It's flat, meaning that there are no delays. Photoionization is instantaneous. However, this phase is centered around pi/2, and this pi/2 truly captures the relative phase shift between the two photoionization events, helium versus neon. It originates by the difference in the symmetry of the two atomic system, the S state of helium versus the P state of neon. And here we can directly resolve that in the lab. And now we can go to slightly more complex interferometer, looking at neon versus argon. The phase changes more rapidly. There are clear delays here, and we can also observe a well-known spectral feature of the Cooper minima associated with the argon photoionization. So just to conclude this part, attosecond interferometry enable us to resolve the full complex properties associated with photoionization or photorecombination events. Once we have amplitude and phase, we have everything. In the next step, I would go from single photon interaction into perturbative nonlinear few photon interaction, where I focus on the unique example of transient absorption. Attosecond transient absorption captures the instantaneous response of a quantum system as it interacts with the laser field. And the main idea is that we send a strong laser field, it dresses the quantum state of the medium, it can lead to dynamical Stark shift, and then we can probe the instantaneous position of these states by sending an attosecond pulse and looking at the transient or instantaneous absorption spectrum. And if we scan the relative delay between the attosecond pulse and the fundamental field, then we observe that the absorption spectrum itself, beyond shifting, also oscillates, and it oscillates at twice the fundamental frequency following the oscillations of our fundamental field. And indeed, over the past 2 decades, attosecond transient absorption has been one of the primary and most successful measurement scheme, leading to the observation of a large variety of phenomena in atoms, molecules, and solids. And all these experiments share one important limitation. They all follow the transient absorption, the transient intensity of the transmitted light, while the transient phase was not directly observed. However, we understand that the complex evolution of quantum wave function should be encoded in the coherence of the transmitted field, in other words, in the amplitude and phase of the transmitted light. And if we want to fully restore the underlying dynamic, we have to find a way to somehow resolve phase information as well. Interferometry enable us to achieve that. So let me go back to the same interferometer I presented before. These are the 2 coherent sources. And now I would add some quantum system in between, for example, helium atoms, and let the strong laser field interact with those helium atoms. It dresses their state, it modifies their transient spectrum. Attosecond interferometry enable us to follow not only the transient phase, not only the transient amplitude, but also the transient phase. So I would go step by step over this experiment. So let's start by switching off the reference arm. So this is a simple absorption measurement. I switch off this source. So now we scan the delay between the fundamental and the transmitted attosecond pulses. And for example, let's look at harmonic 13. We see that harmonic 13 beats, and it beats at twice the fundamental frequency. And this has been observed in a huge number of transient absorption experiments in the past. Now, let's turn on the reference arm, and now we observe interference. I repeat this experiment, and what we see here is a beautiful fringe pattern with extremely rapid oscillations. And this is the interferometric signal. The oscillations are observed at the fundamental frequency in the XUV regime, for example, at 13 harmonic periodicity. If we take a closer look, we see that this fringe pattern beats, and it beats at twice the fundamental frequency. And this beating pattern is really wonderful because it enables us now to trace back and reconstruct both the transient amplitude, but most importantly, the transient phase itself. And here we can extract the transient phase for each delay and follow how this phase evolved within the optical cycle. Okay, so we have the entire complex information of the transmitted light. And then we ask ourselves the following question. What is the additional information this phase provides us? What is the physics that it encodes that could not be directly resolved from simple absorption measurement? And I would try and answer this question in the frequency domain. We can think of transient absorption measurement in the lowest perturbative order as a multiple quantum path interferometer, where each path is composed of at least 1 XUV photon and 2 IR photons. Eventually, these paths interfere when we scan their delay. Their interference leads to the beating at twice the fundamental frequency, which really comes from the contribution of these 2 IR photons. And we can do a Fourier transform. The interference is here at twice the fundamental frequency. We can observe the interference. However, we have no clue what is the individual contribution of each single quantum path in our interferometer. Interferometry enables us to lift this degeneracy. So now, let me go back to the fringe pattern. Now we have full interferometric signal. And if I perform the same Fourier transform, then the information is encoded in the high frequency regime. This is the bright peak, is the interferometric signal itself. It's quite boring. However, the beating, which encodes the dynamics, is encoded in the appearance of 2 super important sidebands. And these sidebands are really important because we can directly link each sideband into the individual coherent contribution of a single quantum path. In other words, we were able to take this interferometer and break it into its coherent pieces. And if I can break this interferometer, if I can distinguish individual quantum paths, then I can take each path and trace it back into the time domain. So for example, we were able to watch the temporal evolution of long-term coherences in neon, which continue to be coherent over many, many tens of femtoseconds. But if we zoom in, we can also watch the evolution of these coherences on a femtosecond and even on an attosecond timescale. So far, I have discussed two fundamental phenomena in nature: photoionization, transient absorption. Both of them are in the weak field regime. Now let's go all the way from the weak field regime into the completely other extreme, where we look at the moment at which a strong laser field suppresses the Coulomb barrier and an electron can tunnel out. Field-induced tunneling is probably one of the most, in my opinion, fascinating, but also important strong field phenomena. It really set the starting point for almost all attosecond scale experiment, and it's also one of the fastest mechanisms we can think of. Intuitively, if we think of an adiabatic picture, then we understand that at the peak of the laser cycle, the barrier is strongly suppressed. So here, tunneling probability is relatively high. A few hundreds of attoseconds later, the barrier lifts up and tunneling probability drops to zero. So the entire tunneling mechanism evolved during a tiny fraction of an optical cycle. And indeed, about a decade ago, together with the NBI team and the group in Bordeaux, we have been able to characterize the temporal window within the optical cycle at which the electron tunnels out. And we have shown that this window spans over about 300 of attosecond, close to the peak of an optical cycle. However, if we take a closer look into the mechanism of the tunneling process, we realize that it is far from being simple. In fact, under most experimental conditions, we don't have a tunneling barrier that follows adiabatically the instantaneous value of the laser field. In fact, as the electron tunnels out, it feels a dynamical barrier. The barrier oscillates extremely fast in time, and as a result, the electron itself is excited not only outside of the barrier, but as it propagates under the tunneling barrier. It is excited under the barrier, it accumulates some initial kinetic energy, it exits slightly closer to the origin, and one of the most sensitive fingerprints of this subbarrier excitation is a phase shift. This is a phase shift that encodes directly the subbarrier dynamics, the subbarrier excitation. And the question is, how do we resolve this phase shift? How do we resolve dynamics, which evolves in the completely classically forbidden region? In other words, how do we put a probe here when the electron propagates under the barrier? A simple way to go would be to slightly tweak the tunneling barrier itself. And we can apply such tweaking if we superimpose a weak second harmonic field on top of the strong fundamental field. Now, this second harmonic field doesn't do much because it's extremely weak. The main effect would be a tiny suppression or a tiny enhancement of the barrier. And now, as we scan the two-color delay, we simply tweak the barrier. And as we tweak the barrier, we change the tunneling probability. And if I stand in the lab and look at the detector, what I see is that the harmonic signal, they modulate as well, following the modulation of the barrier. But such tweaking does not only change the instantaneous position of the barrier, it also changes its dynamics. It also changes its temporal gradients. So for example, if I put my second harmonic field such that its zero crossing overlap the moment of ionization, here what we did is that we slightly increased the temporal variation of the barrier, and therefore we gave an extra kick to the electron as it tunnels out. We gave an extra kick, and therefore the electron accumulated an extra phase. So when we scan the two-color delay, what we see are modulations, which are not only amplitude, but also phase. Here we slightly enhance the excitation or slightly suppress it, and so on. Now, it's quite easy to observe amplitude modulation. Even I can do that. I simply enter the lab and I look at the detector. I don't have to do much. The question is, how do we resolve this very complicated information, the modulation of the phase? At this point, we have decided to bring our interferometer. So now we have a two-dimensional measurement. Along one axis, we tweak the barrier. Along the other axis, we perform a full interferometric measurement. So these are the two dimensions in our experiment: interferometry and tweaking of the barrier. Now let's change the two-color delay. When we change the two-color delay, we see that the signal modulates. And these modulations are dominated by the modulations in the instantaneous tunneling probability. But if I take a closer look, I see that the phase slightly changes as well. And such phase modulations are really wonderful because they directly encode the excitation under the tunneling barrier. We can take those modulations and trace back for different harmonic order the phase at the exit of the tunneling barrier. So here it's a function of energy, but we can also present it as a function of ionization time. It's rather flat simply because the ionization window is very, very narrow. However, it's quite substantial. The phase that the electron accumulates under the experimental condition that we had at the time is about half a radian. So far, we have looked at completely different regimes of light-matter interaction, starting from the very weak regime all the way to the strong field regime. But all these experiments were observed in very simple atomic systems. So towards the last part of my talk, I will take one quite significant step and go all the way from atoms into strong field dynamics in solid-state systems. Strong field light-matter interaction in solid really open up a new and in my opinion, very exciting field of research where we have many, many theoretical predictions. Some of them are still really hotly debated, but only few experimental observations. And one of the most important breakthrough in this direction was the discovery that was obtained in 2011 that we can in fact generate attosecond pulses directly from a solid state target. Now, there are different mechanisms to describe the generation process. I will not describe all of them here. Let me focus on one unique mechanism, which is very similar to the one we're familiar with in the gas phase. At the peak of the laser cycle, an electron can tunnel from the valence into the conduction band. So this is the valence band. This is the valence band. This is the conduction band in a solid. And then after tunneling, it initiates an electron hole wave packet, which propagates within the band structure. It can reach all the way up to the edge of the beryllium zone. It can excite higher conduction band until at a certain point, the electron and hole overlap, photorecombine, and photorecombination lead to the emission of optical radiation with attosecond duration. And when I was first introduced into this mechanism, I was super excited because it tells us that now we can really integrate all the three important aspects in harmonic spectroscopy in order to look at subcycle phenomena in condensed matter systems. And in the following experiment, I will describe how we integrate all these three aspects in order to look at a well-known property in physics, and this is the famous Berry phase. As we all know, when a quantum system performs a closed loop in some parameter space, it acquires a geometrical phase, which is also known as the Berry phase. In condensed matter physics, this Berry phase is accumulated when we perform a closed loop in momentum space. This Berry phase and its closely related Berry curvature are really at the heart of fundamental condensed matter phenomena, from quantum Hall effect, topological insulator, and many, many, many more. However, directly resolving this phase experimentally is very challenging. First, we need a proper interferometer. And then we need this interferometer to be very local. The ability to resolve phase information in a large variety of systems, especially in room temperature, is highly limited by multiple scattering or dephasing events leading to the loss of phase information. So here comes, I think, the beauty of attosecond science. We are able to probe those quantum phenomena. We are able to resolve phase information on extremely short time scale, way before any scattering or dephasing mechanism occurs. And now I would go back to the very basic generation mechanism that I've just described. And if we take a careful look, we realize that the electron here performs a closed loop in energy, momentum, space. And the beauty of this loop is that the Berry phase it accumulates is directly mapped into an optical phase carried by the emitted attosecond pulses. So when I generate those attosecond pulses, the Berry phase is already there. All we need is a proper interferometer to resolve it. And the question is, how do we resolve this phase? In fact, we can resolve this phase if instead of building an interferometer in our lab, we induce such an interferometer which acts on the electron during the interaction itself. And one simple interferometer we can induce can be applied by going from linear polarization into an elliptical one. By changing the polarization of our laser field, we truly shape the path of the electron. And if we change the path of the electron, we also modify the Berry phase it accumulates. And we apply such shaping along the positive half cycle, and then the same shaping just inverted along the negative half cycle. Eventually, the two half cycles interfere in the harmonic spectrum. And due to symmetry, they can have completely different Berry phases, even inverted Berry phases. So they encode the relative Berry phase at the harmonic spectrum itself. And here we consider the specific example of quartz crystal. This is the Berry curvature in quartz crystal of the conduction in the valence band. And here is the path that the electron follows as it interacts with a linearly polarized laser field. And when we go from linear polarization into an elliptical one, we change this path, and therefore we change the Berry phase that the electron accumulates. And now along the negative half cycle, due to the inversion of the Berry curvature, we'll have exactly the same Berry phase, just inverted. So these are the two arms in our interferometer, and one can show that due to symmetry, those two arms interfere in phase for odd harmonics and out of phase for even harmonics. Even harmonics always represent symmetry breaking. In our case, symmetry breaking is achieved by the Berry phase itself. So here are experimental results. This is harmonic spectrum as a function of laser ellipticity. And as we increase the laser ellipticity, eventually the signal drops to zero. And the signal drops to zero simply because the electron and hole become more and more separated from each other, and therefore, at a certain point, there is no photo recombination, there is no overlap. But if you take a closer look, we realize that there is a beautiful fringe pattern here. And in fact, if I compare neighboring orders of even and odd, we see that this fringe pattern is almost completely out of phase. And this fringe pattern reveals the interferometric nature of our measurement and enable us to trace back and reconstruct the Berry phase itself for different harmonic order. Here we see how increasing the laser ellipticity increases the Berry phase simply because we break more and more the symmetry between the two arms in our interferometer. So with that, let me conclude. Attosecond science was born and then evolved at the interface between ultrafast phenomena and strong field light matter interactions. And the first 2 decades of the field, which were extremely successful, focused on light matter interaction and attosecond phenomena, mostly in gas phase systems, and these are atoms or small molecules. I believe that another exciting research direction to go would be to integrate this field with condensed matter physics. And here, most of the phenomena have not been resolved yet. And here we have a large variety of dream experiment, starting from the ability to watch how the band structure itself changes within the optical cycle through multi-electron dynamics or even subcycle topological phenomena. And with that, I would like to thank you for your attention.